Hello, everyone, and a very warm welcome to this webinar where we are talking real-time AI speech enhancement in headsets and earbuds. We will be showcasing the possibilities with AI processing, chip design, and speech enhancement, and outlining where we came from and where we are today with online communication, active noise cancellation, and environmental noise cancellation. Today's webinar is brought to you in collaboration with the Danish Association of Engineers, IDA. Thank you very much, IDA, for participating. My name is Jeppe Lindegaard. I have a background in TV sound engineering and music and sound design. Today, I am the event and project manager here at Danish Sound Cluster. And Danish Sound Cluster is a member organization in the sound industry. We're sharing knowledge, experience, and new research, facilitating relationship building in the sound community, and facilitating new collaborations to boost innovation. And in the panel today, we have Martin Kroon, VP Marketing of Green Waves Technologies, and we have Martin Bergman, CTO and co-founder at Augmented Hearing. Now, Martin Bergman is CTO and co-founder, and oh, excuse me, I left out a slide here that I would just like to address. That some of you who signed up early might have expected to meet Mette Carstensen today, but we are very fortunate that Martin was unexpectedly able to step in her place, because Martin is able to give you an even deeper industrial perspective with his extensive experience, and he's also more hands-on with the tech development. So yeah, thank you, Martin, for joining us. So Martin Bergman has over 20 years of experience in digital audio, AI, and software development. With an MSc in engineering, he excels in spotting tech opportunities that meet user needs. Martin has led numerous initiatives, transforming innovative concepts into market-ready products. His commitment to cutting-edge technology drives his company's strategic vision, ensuring their solutions are both innovative and practical. So thank you very much, Martin, for joining us. Do you want to say hello to the audience?
Hello, thanks for joining.
And we have Martin number two, Martin Kroon, Vice President of Marketing at Green Waves. Martin obtained his BSc in Computer Science from the University of Edinburgh in 1987. After working in several technical roles, he joined the Hewlett-Packard in 1989. During the 11 years there, he worked in marketing roles for both PC, mobile, and networking products. After leaving in 2000, he set up the European operations of a US startup, Socket Mobile. In 2012, he joined Option Wireless, where he held marketing and business management roles in the 3G and 4G data modem and IoT gateway product lines. At Green Waves Technologies today, he's responsible for marketing of the GAP application processes, which I'm sure we'll hear more about today. So in the audience today, we have more than 260 people have signed up, which is turning out to be a record crowd here at the Danish Sound Cluster. We have professional profiles from companies like Harman, GN Hearing, DPA Microphones, Demand, Sonova, Bang & Olufsen, Sennheiser, Huawei, WS Audiology, Siemens, Epos, Grass, Cambridge Audio, Fraunhofer, HBK, and many, many more present people are here, as well as a range of university students from all over Europe. So we want to thank you very much, all of you, for coming today. You are, throughout the webinar, very welcome to leave your questions in the Q&A box. We will address those questions at the latter end of the webinar today and get a good discussion going with you guys and girls. Live polls might pop up in during the webinar, so please don't panic if you see a box coming up. That's just me leaving a question. So without further ado, I would like to just get a quick chat going here with the Martins. Now, Martin Kroon, as a collaborator, because you guys have been collaborating closely, what would you say is Martin Bergman's best skill?
Well, I think I'd comment more about the company as a whole. They're producing solutions which are, at the cutting edge of what people are doing in terms of environmental noise reduction and speaker noise reduction, and it's a key feature for us. We're a chip manufacturer, so we, as I'll explain, our role versus our partners. But it's very key for us to be working with the companies that are doing the best stuff in the world.
All right, and likewise you, Martin Bergman, what would you say is Kroon's best skill, or maybe GreenWaves in general?
Yeah, we've been working with GreenWaves for, I guess, 2 years by now, and it's a company we really admire. That's no secret. It's really amazing to have a European company on the forefront of deep learning, edge AI chipsets. We are honored and very happy to be working with GreenWaves. So I wouldn't pick one best skill, but I think people will be very impressed with Martin's presentation, and the capabilities of Cat9 is really a groundbreaking part. Yeah.
Thank you, Martin Bergman. And from now on, I think I'll just be calling you by your surnames, so the confusion won't be total here. For those of you joining us a little bit late, I can see people are still joining us. We're talking about real-time AI speech enhancement in headsets and earbuds with Martin Kroon, Vice President of GreenWaves, and Vice President of Marketing, at GreenWaves, and Martin Bergman, CTO and co-founder of Augmented Hearing. Now, before we kick things off, Martin Kroon, I have another question for you. What do you think is the most important skill set as a collaborator? Professional skills or people skills?
I'm not sure that I'd put it between professional skills and people skills, because I think both are very important. I think the most important thing is that there's a fit from a cultural perspective between two companies. When we work with partners, we have a company kind of way of being, and I think it's very important that that works well with our partners, and that we can collaborate. We tend to be quite open in our collaboration. We think that as a startup in the semiconductor business, we can't act like everyone else, and we want to have that openness with a partner. So the more open a partner is with us, the more we can help them, and I think that's probably the most important thing with working with partners.
All right, and Martin Bergman, what's the most fun about collaborating that you don't get when you work alone?
Yeah, the most fun is that you work with people like GreenWaves, and you look at what they have done, and you just think this is just so incredible, and you can see together you can do something that's so much bigger than the sum of its part. That's sort of the most fun to me, that you see the potential. Yeah.
All right, cool. I won't drag this any longer. Mr. Martin Kroon, Vice President of Marketing at GreenWaves, will you please take the floor and share your screen and enlighten us all?
I'll try. Thank you very much for the introduction, Jeppe. Hopefully you can see my screen now.
Yes, looks good.
Okay, so I'm going to give you a quick overview of GreenWaves, who we are, what we're doing. It's going to be a little bit sort of processor stuff. I'll try and make it intelligible. but kind of sort of set the stage for the platform that Augmented Hearing have been using to deliver their stuff. And then I'm sure Martin B will do a much more interesting presentation for the audio side of this, because he'll be really focusing on the audio features. I'm going to look at really, you know, what does the platform look like, and what are the facilities of the platform. So GreenWaves is what's known as a fabless semiconductor startup, which means that we design and sell chips. We don't actually make them, because there's very few companies in the world that actually make the kind of chips and the technologies that we use. There's about 5 that you can use. We've been running since 2014, and our market area is really high performance processors, but for very, very energy constrained devices. And I'll go into, you know, how we do that. We're currently 45 people. We're mostly in Grenoble in France. We have some offices in Bologna, technical offices in Bologna. We have a very close partnership with a couple of universities, the University of Bologna in Bologna, and ETH Zurich, which is a technical college in Switzerland. They jointly have a program called PULP, which our CTO is one of the co-founders. PULP stands for Parallel Ultra Low Power, and it's basically a program looking at, you know, research around using parallelism to lower the power in semiconductors. Then we have a group in Denmark, in Copenhagen, of 3 people. And we also have a sales office a sales and FAE office in Shanghai, who looks after our ODMs. And then we have agents around the world selling our products in the US and other regions. One of the nice things, GAP9 is our 2nd generation product. We did our first product, GAP8, which was in production in 2020, and GAP9 has entered into production at the end of last year. GAP9 is actually produced by a foundry of an American company called Global Foundries, but they have a foundry in Dresden in Germany. So GAP9 is actually a processor that's entirely designed and produced in the EU, which is, I feel that that's a nice thing. Obviously doesn't change the product. So as I said, our focus is this high performance computing in a very energy constrained device. So what kind of high performance computing? And there's really kind of 3 things that we bring together. And we bring them together that's in a way that they can be used together. One is very, very low latency DSP processing. Then there's general DSP, digital signal processing, and finally, neural networks and machine learning. And across these 3 kind of things, we try and bring basically 3 different points. The first is to keep flexibility. When you're trying to make something very, very low in energy, the easiest thing to do is lose flexibility. And so we try and keep that flexibility of the solution while keeping the absolute low energy point. And when we talk about low energy, a lot of people talk about low power, and they say that they're low power. Well, you can be low power and draw a watt. But what we try and target is really absolute low power in terms of the kind of energy constrained devices that we're going into. And really there, it's a mix of wearables, hearables, and some IoT segments, the IoT market, particularly in medical and security. And then the final point that we try and bring is to keep something which is relatively easy to program. These are deeply embedded processors. I don't think any of them are easy to program. An MCU is not an easy thing to program because it's quite a hidden platform. But we try and keep as much ease as possible and try and keep as much visibility on how the chip works and how the software works on it, so that you don't have hidden surprises with blobs that you don't understand. Then we apply these things to a variety of different types of application inside these products, doing things like data interpretation, object detection, scene detection, face and voice ID, data transformation, things like denoising, which we're going to talk a lot about today, sound effects and visual effects, and then kind of hybrid DSP neural network stuff, where we apply low latency DSP plus neural networks in things like adaptive active noise cancellation, beamforming, and AI beamforming and pickup, and then some pure DSP things like spatial audio that we bring on the platform. And all of these things we bring through partners. So kind of wrapping the chip up in a in a nutshell, there's kind of three different elements that do processing in GAP. The first type of processing, as I mentioned, is this low latency processing. So that's real-time, streamed, time domain, sample by sample signal processing. And there we use a device that we call a smart filtering unit, and I'm going to talk a little bit about what that is and what it does. The second area is the general digital signal processing, and there we use a resource that we call the cluster, and I'm going to talk about what the cluster is and what it does. And within that cluster domain, we use the cluster both for this digital signal processing, but also for a certain portion of the neural network processing as well. And we mix that in within the same kind of domain inside the chip with something which we call NE16, which is a neural network accelerator. So we use both the cluster and the neural network accelerator for neural network processing. And finally, as I said, you know, we aim for this ultra low power point focused on energy constrained devices and try and keep the flexibility and the programmability. You can see the chip up on the right hand side. It's a super small package. It's 3.7 by 3.7 wafer level CSP package, so chip scale package. So it's a really small thing that can fit into these kind of products. This gets a little more detailed about the architecture, and I'll spend a little moment on this, not go too deep into it, but try and give you a kind of feel for the chip and why it's a slightly different architecture to what one traditionally has inside the DSP. GAP is kind of divided into two halves. There's what we call a fabric controller half and then a cluster half. The fabric controller half, you can really think of like a kind of classic microcontroller. There's a core, which we call the fabric controller at the bottom. All of the cores inside GAP are based on an open source standard called RISC-V. You can think of RISC-V as a competitor to x86 and to the ARM instruction sets. One of the nice things about RISC-V is that it allows us to enhance the instruction set, and we do that in a number of different ways in DSP operations, in vectorization, in bit manipulation, and in floating point operations. All of these cores can handle floating point in multiple different variants, 32-bit and 16-bit, and in fact, two different types of 16-bit floating point. And actually, there's 10 of these cores inside the 10 of these cores inside the chip. I saw a question about low latency, what is considered to be low latency, and I will cover that. So there's 10 of these cores inside the chip, and in fact, they all are exactly identical. They have the same resources, and they see the same memory map. And this really makes things very simple in terms of compiler tool chain. You have one compiler, you compile your program once. When you write a function, it can run anywhere on the chip, and the only difference will be the performance it sees to memory. The other things on the left-hand side of the chip, we have some quite sophisticated interfaces, including a camera interface, and also 3 different serial audio interfaces with up to 16 channels TDM on each audio interface, and then up to 9 PDM connections out and in and 3 PDM connections out. And then a number of other different interfaces that you find on microcontrollers, I3C, I2C, SPI, and so on and so forth. We also have an external memory bus on which you can hang external flash and external RAM. It's an LPDDR interface. Then we have a memory block inside the chip, which includes 1.5 megabytes of RAM and 2 megabytes of non-volatile flash equivalent called EMRAM, which is available in the process that we're using. So that really kind of has, and then the other thing which is inside that domain is all the power control. So all of the power control for the chip is actually on chip, and that allows us to do lots of different very fast power changes and power state changes. We use something called dynamic frequency and voltage scaling, which means that you can change the frequency of the chip, that the chip is operating dynamically, and that allows you to then drop the voltage at which the chip is working. By dropping the voltage at which the chip is working, you get an ability to actually reduce the power consumption. On the right-hand side, there's something that we call the cluster. So the cluster is 9 RISC-V cores with a shared memory area. So you can think of these 9 RISC-V cores as each one being able to parallelize some kind of algorithm that you're running on here. And we can parallelize in lots of different ways because these are real cores that are running independently. This is not a structure where you're taking very, very long instruction words and running things through things in parallel. And that way, each core is running on its own. And that means that you need to be able to synchronize them. And we handle all of that synchronization in hardware as well. And then finally, you can see on the right-hand side, the NE16 AI accelerator. On the left-hand side, one thing which I missed out, which is the SFU. You can see that placed very close to the interfaces. That's because the SFU can actually run directly from an interface, produce samples out to an interface. So it can be completely independent from the rest of the chip. So what are the key energy savings that we can get by actually doing this kind of parallelization inside this kind of cluster structure? One of the key ways that you see DSPs operating is essentially operating on very long instruction words where there's multiple different items, compute elements inside the chip. And all of those elements are given a single instruction in a single cycle. So they're all essentially lockstep. And that can be a problem sometimes because there you're relying on the compiler to be able to kind of schedule the instructions all at the same time so they all run at the same time. With the cluster structure, they're actually synchronized, but they're free running. So they all have their own program counter. They can be doing their own thing. And that gives you the ability to do multiple different types of ways of parallelizing. The first is you can just all have every single core running the same algorithm more or less on different data, and you parallelize like that by dividing up the data. But sometimes that doesn't work. There are algorithms where one iteration on the data depends on the previous iteration on the data, and that way the only way you can parallelize that is to start pipelining things. And you can also mix these strategies together, and that allows us to be very effective at parallelizing everything from the neural network type stuff to an FFT or even to an LC3 codec. All of this can be run on this cluster with this kind of parallelization structure. Now, once you parallelize something, what you're trying to get out of that is to speed the thing up. Obviously, you've got 8 cores now doing the same work. You want to get 8 times faster, which is generally known as a speed up factor in the industry. Well, how we use that speed up is that to do the same task, we now need less cycles. So then we can tune down the frequency so that the processor operates at a lower point. And because it's operating at a lower frequency point, that means that we can take the voltage down, and you get a quadratic benefit in terms of energy when you lower the voltage inside a chip. And that's how we the main way that we get this power benefit out of parallelization. Obviously, there's tons of other details that I could go into, but that's the main way that we get stuff out of this parallelization. I mentioned this NE16 resource. So what's that? Well, NE16 is a neural network accelerator. So it handles things like convolutions, which are key building blocks in neural networks, and matrix multiplications. And it does that in fixed point arithmetic with a variety of different input and output sizes. So it can handle 8-bit and 16-bit features, and it can handle everything from 8-bit down to 2-bit coefficients. And it scales as you change the coefficient bit width in both performance, and also obviously you're scaling the number of the amount of data that you're transferring to and from the accelerator. It can do a lot of work. It can go up as far as 308 max per cycle at 2.2-bit coefficients. And the chip is running at 375 megahertz. You can see that that's a huge amount of gigamax per second, up to 123 gigamax per second. But at the same time, being very, very, very energy efficient. One of the other things I didn't really mention when I mentioned the slide at the beginning is that we don't actually use something which is very, very common inside an MCU. Normal MCUs and normal processors is something called data caching. So this is basically when you access some data, you obviously want to actually have that data as close as you can to the thing that's going to be processing it. And that's very, very high speed memory that's very close. So inside the cluster, there's this L1 memory, which is very close to the processing elements, very fast. Very fast memory, however, takes up a lot of space. So it's expensive. And as you get further away from that very fast memory out to L2 memory or even off-chip memory, the memory gets much cheaper and much higher capacity. So you can have a large memory, but at the same time, it's slower and it uses a lot of energy to transfer stuff from it. So normally in these kind of chips, you have a kind of automated scheme where data is kind of brought up through these memory hierarchy to the processor. Unfortunately, in the kind of things that we're doing, streaming audio, that becomes very expensive from an energy perspective. In fact, what happens is that you load stuff into this cache and it tries to predict what you need and loads pages of stuff into it. But unfortunately, in a streamed kind of architecture, it turns out that you get a very low cache efficiency. That is, you load stuff, but then you don't use it. And in fact, it can be as low as 30%. You're only using 30%, which means you're throwing away 70% of the data that you loaded. Again, that has a huge effect on energy efficiency. So we use software tools to create streams between these different memory areas and can create a program, in fact, write the program that you need to actually stream data. And we do that at the point where you compile your program. And that means that we're very efficient because we've pre-planned all of the memory movement across the chip hierarchy, memory hierarchy. And that's a very key portion of our tools. And all of that, all of those tools basically produce C code that you can debug, that you can see, which gives you lots of visibility. And that cuts down your development time because there's no black boxes going on there. What does all of this deliver in terms of neural networks? Well, it delivers very low energy performance. There's actually a dearth, there's not that many benchmarks around for this kind of low-powered machine learning on these kind of products. One of the benchmarks that exists comes out of ML Commons. It's called TinyML or ML Tiny benchmark. And here you can see results in terms of both latency and energy against the nearest other chips that are delivering, in our kind of energy class. It must be said that this benchmark is on very, very, very small networks, and they're networks which are way smaller than the kind of networks that we're dealing with when we're doing things like denoising. But you can see that we're delivering 2 to 3 times less energy than a highly specialized neuromorphic chip, and 2 to 4 times less energy than a specialized neural network accelerator chip, and at the same time delivering the lowest latency there. As I said, benchmarks are difficult to come by, and actually most of the benchmarks are in the image world. So this is actually a load of different image things, but they're interesting to have to compare us to different chips. Again, this is showing the number of cycles that we take to process something, our processing efficiency, essentially the number of multiply accumulates that we can do per cycle, and then the latency of executing one iteration on those networks, and the energy that we deliver at the end of that. There is one audio network at the end of that, which is YAMNet. It would be lovely if someone came up with a benchmark around audio. It doesn't exist at the moment. So how do these neural network capabilities apply specifically to sound? There's kind of 3 different levels, I think, of neural network processing that can go on in sound products. The first thing is kind of classification tasks. So this is simple things like acoustic scene classification, figuring out what kind of environment are you in. They're relatively low load. There's a lot of different chips that can do them and do them pretty well. On GAP, these are kind of things you almost get free of charge. They're very small networks generally, and we can run them very, very efficiently in the background. Then there are things like the denoising problem, where you're using much higher load neural networks. And most important, these networks are what's known as regression networks rather than classification networks. In a classification network, you're just coming out with, it's a dog, it's a cat, or it's a person, it's not a person, or something of that sort. In a regression problem, you're taking noise in and producing a floating point, well, at least a progression of number point filter that you're trying to apply to the sound. And that is a very different thing to those first types of problems. And then finally, there's a thing which GAP brings in, which is this ability to actually take a very, very low latency filter like an ANC filter and apply neural networks not to doing the task, because it would take far too long for a neural network to process. It wouldn't work within the context of an ANC primary path filter, but using the neural network to actually adapt the coefficients of the filter for the ANC. And that's where I think GAP is pretty unique in terms of our ability to do that. And we do that in this thing called the smart filtering unit, which you saw in the first architectural slide. Kind of sits very, very close to the interfaces. What is it? Well, it's basically a configurable audio graph processor. It can run multiple different graphs. Those graphs can take their inputs and outputs from the memory, from interfaces. So you can process directly from a PDM in to a PDM out, or you could process from a PDM in into the L2 memory area, or from the L2 memory area out to a PDM out, or you can actually use it almost as an accelerator, just processing blocks of data from the L2 memory to another block of data in the L2 memory. Once it's at an interface, it's really processing sample by sample, which means the moment that a PDM sample has been decoded, and inside the SFU, there are PDM modulators and demodulators. The moment a sample has been decoded, it will start being processed, and it will be pushed out through the output interface. There are a number of different blocks in this, which are all hardware blocks that are highly configurable hardware blocks, including a key block, which we call a global filtering unit. The global filtering unit implements a number of different filter patterns which can be inserted into the graph. But there are things like asynchronous sample rate converters, splitters, mixers, resamplers, and so on and so forth inside the product. It's really, focused on the original motivation for this was ANC, and it actually is capable of processing, a typical ANC graph, 768 kilohertz, 32-bit in real time, which gives it a structural latency of about 1.3 microseconds. And then the second thing is obviously to get, good power consumption. If you do this kind of stuff in a DSP structure, or a specialized DSP, generally the power will not be at the same level that we deliver, because you have some overhead in that kind of structure that we really don't have. And then the final thing, which is very, very important, is for this thing to be deterministic. So, it's completely independent, it has its own memory, it has its own resources, and that gives it the ability to really process on its own. And we focus this towards ANC, heavy-duty filtering, sound spatialization, sound effects, and so on. This is a list of all the different features, filters that are inside that GFU. You can see there's a huge number of them, and each one is highly configurable with lots of different parameters to it. This is showing, I'm not going to go into the details of this, but this is showing mapping an ANC graph into GAP, and you can see that we can map a large portion of the graph into the SFU area, while having other bits in software running on the processors, either on the cluster or on the fabric controller, and actually directly communicating out with the SFU via its splitters, splitting data and writing data into the L2 memory area. All of this stuff is great, but if you don't have a decent way of actually using it, then that's a big problem. So we spend a lot of time, have actually more people working on software than we have working on hardware. And we really deal with kind of 3 different communities of developers who all have different tools that they're used to using. Audio designers, they use MATLAB. More and more of them are using Python, but it's basically MATLAB and tools like that. And there we have a number of tools like MATLAB simulations of all the filters that are inside the SFU, the ability to, design your filters inside a MATLAB environment and then export the parameters and produce the configuration for the SFU to actually, run those filters. Then we have tools which are for data scientists. So data scientists, generally, it's going to be things like TensorFlow or PyTorch. And then we have tools that take the interchange formats of TensorFlow and PyTorch, which are things like TF-Lite and ONNX, which are essentially export formats, and take those, process them, and then produce C code that you can run to run those graphs on GAP9. And then finally, we have application developers, and there you program GAP9 in C or C++, and we have a pretty standard GCC open source tool chain that allows you to build those applications. And the unifying point of all of this is basically C code. All of these tools are producing C code, and then we have a runtime that we call PMSys, which is a lightweight runtime based around FreeRTOS that allows you to actually run your code on the platform. Once you've actually got something compiled, you can either run it on the chip, obviously, but we also ship a full SOC simulator, which gives you a kind of view inside the chip, and you can see these kind of wave graphs of showing exactly the activity that's going on inside the chip, and it makes it a very productive environment. We've had a tier 1 audio brand who's told us that we do in weeks with Gap9 what it takes us months with our current supplier, which we were very proud of. But we do think that using this using this SDK is pretty easy and pretty visible. We have a horror of black boxes, and we try and keep away from them inside this, so you get full visibility of exactly what's happening in the chip. And finally, we have lots of different audio development boards with the chip on it, with audio interfaces, and even a small audio demo board that you can use for building prototypes with the chip. So key things to take away. I think audio neural networks combine several attributes that make them very different from other networks that we've dealt with, particularly with the image size of the neural network side, neural networks. Many are regression rather than classification problems, and there are a lot of techniques for compressing networks like quantization that work well on classification problems, are much more tricky on regression problems. One of the things that we bring with Gap9 is this ability to have networks working in multiple different precisions in float and fixed point, even within the network itself, and that is crucial for these kind of problems. Quantization flexibility is a must, and in fact, overall platform flexibility is a must. Many audio networks are facing latency targets that require them to run very often. So particularly if you think of denoising, you're inside the signal path, you have to run really often, otherwise the latency is too high. And the total load of that can be really high, even compared with image networks. Tool use and flexibility are extremely important so that you have reasonable development time and you can use all the features in a chip. And there's a lot of opportunities, we think, that come out of the combination of using this neural network ability along with the SFU and being able to dynamically change the coefficients of a running SFU graph. And that brings a lot of opportunity in adaptive beamforming, adaptive ANC, and combining these things together. And finally, our strategy is exclusively to work with software partners. We produce demos of things that we do, but they're mostly stuff that we find on the internet that we put onto the chip, or things that we do from a prototyping perspective. But we have partners that go everything from algorithms and specific algorithms for specific topics like augmented hearing, to complete reference designs around Gap on earbud or banded headset devices. And so that kind of leads me into passing the stick to Martin to talk about augmented hearing and what they're doing with doing on Gap9. Thank you.
Thanks, Martin.
I'll stop sharing. There we go.
Yeah, you can see my screen. Yeah,
Yes.
Thanks, Martin. It's really incredible what Greenwaves is doing. We are big fans, as I said. And I'll talk a little bit about augmented hearing, what we do, and how we see real-time AI speech enhancement. And in the end, I have a little announcement about Greenwaves. So stay tuned. Don't go anywhere. You'll hear it here first. So if we take a step back and look at traditional audio digital signal processing, which has been used for several decades now, it requires careful tuning to hardware and use case. Algorithms do not learn from data, and you have to have specialists who tune the algorithm to specific use case and hardware. And we all know that you have limited abilities. Speech in noise is still an unsolved problem, like the cocktail party problem that Martin talked about. maybe sort of stationary noise can be removed, but when you talk about complex noise, it's still not solved. So what about AI speech enhancement? Well, it's basically using AI to improve the speech quality, intelligibility, and reduce or remove noise in real time. So when we talk about AI, it's obviously not AI that can pass a bar exam or do your homework. It's more like Martin described, it's a digital filter that has learned from a vast amount of data and can then provide very precise parameters to enhance the speech quality and remove noise from a noisy signal. And we are looking at a lot of use cases. I'll go into some of them, but you can imagine there's critical communication as a segment. It includes emergency calls, defense, air traffic. There's voice calls, video conferencing. There's also this transparency mode, which you probably know from earbuds and headphones, where you're wearing your headphones, but you still want to interact with people and talk. Then there's hearing protection. Of course, when you wear hearing protection, you don't hear anything, so you cannot talk to your coworkers, and then you take off your hearing protection and then you have no protection. So ideally, you would want hearing protection and be able to talk to your coworkers. And live broadcasting is another use case, obviously. So just quickly about augmented hearing, we are founded in 2021. We are a hardcore software development company. You see my co-founders, Mette and Christian, and we have Jes as our chairman. And we have a highly talented team, which it's a privilege to work with every day. So, and right now we are working mostly in critical communication. So we say we clarify speech in the most demanding situations. And what are those? This is, for example, 112 calls. So you can imagine someone calling from a noisy road or concert or a baby screaming. Then the operator can choose to reduce the background noise, to focus on the speech and to reduce the fatigue and stress that comes with this job. We have our software running now in Greater Copenhagen. So if you call 112 within Greater Copenhagen, the operator can then access our software. We're also working with defense, communication systems in defense, and we are working with air traffic management, where you have communication between the pilots and the control towers. And there you also have an analog system, which is also very susceptible to handling noise. You have the old ALO coding and so on. So it doesn't sound good, let's put it that way. So a little bit about our core technology and how we see it and how we test it. So we have a comprehensive test and training setup. Most of it is running in PyTorch. And all training is done on premises. So we have our own training computers, and we can train to different use cases and different model sizes, obviously. And on the inference side, we have our own highly optimized inference engine written in pure C with no dependencies. So this enables us to optimize to different CPU or GPU architectures. We have optimizations for Intel and ARM. We also use SIMD, like Martin talked about. And the rationale for having it in pure C with no dependencies is that then it's much easier to port to different systems and different platforms. So our software can run on almost any system that has sufficient memory or compute. So this we have it running on Apple systems, Windows, Linux, Raspberry Pi. So if you can imagine, if you have a cloud system, then you can handle all the dependencies there on that. But if you have to install your inference engine in customer systems like we do, you have to be extremely flexible with regards to also the audio configuration, sample rate, frame size, and so on. And you don't want to compile a lot of complex dependencies which may not be supported on the customer system. So, yeah. So, and an important thing is how do we actually test that it's working? You can listen to it and say, oh, it sounds a little better, but obviously that's not very reproducible. So, of course, we use metrics, as many of you probably also know about. So here you can see a model that has processed different speech signals and mixed with different noise types and in different SNR. So yeah, so you can see the noise types down at the bottom, and the SNR, the signal to noise ratio, goes from -5 up to 10 in a few steps. And this is the signal to distortion ratio metrics. And you can see a good improvement across all noise types and different SNRs. And there's a few different metrics because no metric is perfect. So some metrics have different pros and cons. So we also use the PESC, which is a more perceptual algorithm that tries to mimic how a human would rate the sound quality. And also here you see a good improvement with this model. Sorry. And same with the Story, which is often used in the hearing care industry. So yeah, that was a little bit about how we test. And now we go to the announcement, because we also want to talk a little bit about GreenWaves. And we have a new speech enhancement model for GreenWaves. It's available today. And the use cases are, Martin mentioned face-to-face communication. And this is a very challenging use case where you can imagine you are in the real world. Imagine that at a cafe or restaurant, and you want to attenuate background noise and hear more clearly what people are saying in noisy conditions. We can do environmental noise cancellation. So this is, for example, when you do a phone call, you are in a noisy place, the noise is reduced on your side, on the microphone. And then we can also do fine speech enhancement. So if you talk with someone on the phone and they are in a noisy place at a freeway or somewhere, we can enhance that speech. Yeah, and I can say that we have state-of-the-art metrics. So basically the GAP9 can do state-of-the-art speech enhancement, which is incredible for such a low power device. We can go down to 5 milliseconds algorithmic latency, which means, I'm sorry. And it's available now at GAP9. So that's pretty cool. So to summarize, AI is really revolutionizing speech enhancement. We at Augmented Hearing is laser focused on solving the problem of understanding speech and noise. And we are happy to announce we have the state-of-the-art speech enhancement with Probably one of the most complex models running on such a small device available with low latency available today. So yeah, that is my presentation. Stop.
Okay, Martin Bergman, thank you very much. Yes, and thank you for stopping your share screen. Thank you to the Martins, Kroon, and Bergman for your very insightful presentations. I'm sure a lot of people have followed with great interest. Now, this is where we have time to take questions from all of you. So please leave your questions in the Q&A. I will be kicking off the party here with just a couple of questions for you, gentlemen. And I'd like to start with you, Martin Kroon. What has been the biggest practical constraints you've met in your process of developing Gap9?
Whoa, the biggest, largest. There are lots. I mean, to start with, you know, when we tape out is when you send the chip to the plant to be fabricated. When we started with Gap 8, you know, we taped out when we were 10 people. So the biggest constraint was not having enough people. And you know, making a processor is probably one of the most difficult things to do, because a processor lives and dies on the tools that are around it. A processor is absolutely useless unless the tools are great. So I think probably one of the big challenges has been, you know, getting the tools to the level where they are now in terms of the productivity that we can deliver to someone using them. Then, you know, on the chip side, I'm not a chip designer. I'm much more on the software side than I am on the hardware side. So I can't really comment to chip design. But you know, I mean, again, as a small company, you know, semiconductor is a business where you press the compile button, you send your chip off to the fab, and when you press that compile button, you spend multiple millions of euros. And if you get back a chip that doesn't work, you're dead. So you know, there's some challenges there as well. So I think and there's some challenges there in terms of, you know, being a startup in Europe and raising the kind of money necessary to do those kind of things. So I think there's multiple challenges.
Right. And is there any challenge or constraint that you kind of predict in the future that might be even bigger?
I think, you know, I mean, obviously there's a huge amount of noise around at the moment about you know, generative networks and their use in lots of different areas. Actually, we're seeing, you know, it's funny, we're seeing some of the techniques that we used already to compress neural networks starting to be used on generative networks. And you could think of, to a certain extent, the kind of stuff that we're doing with noise reduction as generative type networks, because they're actually generating, you know, audio filters. So we're already bringing some of that technology, but there's definitely, you know, some larger stuff there that we would like to see, you know, coming down to these kind of size of platforms. But that's going to be super challenging. You know, the data that's involved in those kind of things, the size of the parameters is huge. And so we've got some challenges with managing that, but that's definitely within our vision that we take those kind of things and bring them into this kind of low power space.
Right. Okay, thanks, Martin, for your answer there. Before I jump to some of the audience questions, I have just one for you, Martin Bergman. You were talking a little bit about testing, and I was wondering what your role is in a hardware product testing and implementation process. What does that practice look like, and what is your role in that process?
Well, when we work with OEM partners to optimize their devices, so typically involves us in understanding the acoustic chain they have, so we can make sure that all the neurons are spent optimally to ensure the best neural network performance. So that's probably where we work most with partners. Otherwise, as stated, we are like hardcore software. So we tend to work only in the software domain. And also our current algorithm it's a pure software algorithm. So all the improvements you saw on the metrics is pure software. So anything that can be done on the hardware side, it comes on top of that. So, yeah.
All right, thank you. I have a quick one here from René Johannesson to you, Martin Kroon. Have you looked at active occlusion cancellation, AOC?
The answer is absolutely not. No, we haven't, as far as I know. Definitely, maybe my Danish colleagues would say, Martin, but we're doing it already. But I don't think we have, and I'm not sure that we have a partner that's doing it. So if there's someone who's doing that, who's interested in using our chip, then please feel free to reach out to us. It would be very interesting to talk to you.
All right, thanks. Okay, so I have quite a long question here. I don't even know how to sum it up. So
I've actually read it. So
right.
I think
okay. The audience haven't seen it. Do you have a chance to sum up the question, perhaps?
Yeah, I think basically this is looking at adapting a network on the device. So basically training on device, which is on our kind of devices, which is a big topic. I would say it's a big research topic at the moment. We actually have a researcher who's worked on and off for us, Manuele Rucci, who's actually currently working in Leuven. Who's doing a lot of this kind of stuff, and we have done back propagation on Gap9 and had networks actually train on Gap9. There's also kind of things which are sort of close to that in terms of doing things with dual networks, where you have a network which is learning to generate a long number, which we call an embedding in the neural network space, and you feed that embedding into another network, and that somehow controls the activity of that network. And the classic way that embeddings are used is for Face ID or Voice ID. And essentially what that gives you is essentially one network you can run to produce an embedding which encodes a particular person, say their voice or their face or whatever it might be, and that is driven into another network to modify the behavior of that network. But the full adaptation and training of a network on device, probably the most difficult thing is actually much more about the use case, in the sense that if you want to adapt the network, then you're going to need to have some sort of labeling for the thing that went wrong. So you need the data, but you also need, this was good, this was bad, or this is red, or this is blue, or this is a dog, or whatever it might be, whatever the label is, right? And it's difficult in some situations to get that kind of label. There are other things which are used in activity, in fault monitoring for machines and things like that, where you're monitoring sounds from a machine, and you try to do something which is around kind of steady state. So you try and kind of cluster what is the steady state of this machine in terms of all the features that you see coming from it. And then when it goes outside that steady state, which you've learned over a period, then you go, okay, well, it's gone wrong. It's generally known as anomaly detection. There's all sorts of techniques to do it. But as I said, we are doing stuff like that. We've got active projects to do that. There are some clever tricks that you can play in terms of training subsets of the parameters of the network rather than training the whole network. There's lots of different things that you can do in that area. And there's a lot of research on that topic at the moment.
All right, appreciate that long answer to a very long question. I think that was very appropriate. So thank you, Martin Kroon. I believe this one might be for you, Bergman. There's an anonymous attendee here asking, do you have a speech enhancement product for the PC to help with reducing noise and improving the speech on the listener side, especially when having online meetings in, for say, Microsoft Teams? I'm guessing some kind of plugin or something.
Yeah, so I guess he means like the font. Okay, yeah. No, we don't have that. We did consider doing solutions for video conferencing, but it also seems that many of the products, they have built in their own solutions, and I don't know how well they work, but it's we talked to people within video conferencing at some points, and they were not very focused on the quality of sound, I can tell you. They were more concerned about other things, scalability and all sorts of stuff. But yeah, but maybe it's worth considering revisiting that area.
I'm not too surprised, sorry to say, about that answer, but maybe the challenge here is they have their own noise reduction technology, so maybe, you know, that might be a bit difficult.
Yeah, they have something built in, or they bought something, right? And we also talked to many companies doing video conferencing, and most of them were not audio. There's no audio through. What's the problem? I was not so concerned with that.
Right.
Yeah, it is. It's worth mentioning that the the audio that goes off to those servers is at some point it comes out into the plane to get denoised. So your voice is on a server somewhere, which for some people and some companies is not really very acceptable. So local solutions like having it on a headset or having it on the PC could be, I think, a good solution for some people, even if the platforms have denoising built into them.
Right. That's a good point. Okay. I have one coming in here, a question for you, Martin Bergman. Do the AI noise reduction use cases of your new model, face-to-face, far-end voice enhancement, etc., require deployment of multiple specially adjusted versions of the same model? Or is it more of a one-fits-all model? It's a question for Lorenz Adrian.
Yeah, it's a very good question. I think you could deploy the same model as one size fits all, but there might be a little performance benefit from having separately tuned models, especially when we are talking rather small models. There might be a benefit in sort of a slightly specialized models, one for face-to-face and one for the communication. Of course, there's also the practical that you have to load different models, and there's a more complex implementation that's more simple if you deploy one model, which is sort of good in everything, but you lose a little bit maybe by having that generality.
Yeah, I guess also that there's a different latency that's required for both of those tasks. So the face-to-face is far more challenging on the latency side. So if you want to optimize your energy use as well, then you might want to have a different model that you're running slightly slower.
Yeah, that's a good point. And also for the phone communication, as you say, you can use a little bit more latency, and you get a little bit better speech enhancement performance.
Yeah, it gives you a bit more context.
Exactly.
Yeah.
And it doesn't run as often.
Yeah, and it's worth saying that Gap9 basically is a programmable chip, so you can just load the models as you wish. And in fact, our toolset allows you to run models simultaneously. And very often with these kind of noise reduction networks, which tend, some of them are quite big. It depends on the. I think Augmented Hearing done a great job of reducing the size of these things. But we've done other networks where we're actually doing music from voice, active voice separation from music or things like that, which are much bigger networks. There, you could have a network running, but then you've got another network that runs very often that's real-time critical that you really want to run. And what we can do is kind of break one in the middle and run the other, and then go back to the first one. And we've done that with multiple customers having multiple networks running.
All right, so we are moving very quickly towards the end of this webinar, but I have just a couple of questions left for you before we say goodbye. Now, Martin Bergman, it seems that the biggest new step here is the real-time factor, that you are able to do noise cancellation real time. Do you see any next big step you aim to take in your future developments that will kind of be a new breakthrough?
I think, this AI speech enhancement has been around for a few years, and it's been improving a lot in the last couple of years. If you just go back a few years, it's a completely different game. But what I think will happen is that maybe the raw performance will improve a little less in the future, but I think the models will get smaller. So you have the same performance as you have now in even smaller models. So this allows you to use less power or run on even smaller platforms than Gap9. And I also see you will right now we use single channel speech enhancement, and I think we will see dual channel or multi-channel AI speech enhancement also, so that you have a little more hardware to improve. So we are probably reaching the limits of single channel speech enhancement. There's still some performance improvements, but I think it's gotten really good. So there's also there's a physical limitation to how much you can improve a really speech noisy signal with only one channel.
All right, thank you. The last question for you, Kroon. Do you see any unexpected new business area that will benefit from your latest progress here?
Unexpected businesses we've seen a lot of unexpected businesses. I mean, it's part of being a startup. I guess one of the ones which I found quite an interesting one recently was smart pills, which has nothing to do with hearables, but it's pills with cameras in it that you swallow, which were inside one of those. So that was a surprising one for me. We hadn't really anticipated that market at all, but it's very nice when you find a market like that. But I think on the hearable side, I still think that the form factor, question is still not solved, right? I mean, we've just one of our customers has just launched a product in China, Clear, which is an over-ear true wireless stereo headset. So it's one of these ones that doesn't go into your ear. Be interesting to see how that does. It's done that segment has done very well in China, not so well outside China yet. It'll be interesting to see how that scales out around the rest of the world. I think there are other form factors, so I'm really excited about different form factors that we can bring. Either hearing enhancement for people who don't hear so well, or music, or whatever it might be, or combinations of both. I think there's lots of different form factors, and I don't think wireless earbuds is the end of the story, really. So I think that's for me the most exciting things happening.
All right, I appreciate your insight, Martin, and I can tell you that we are looking into doing a webinar about open ear hearables at some point, so please stay tuned. Yeah. Now, with that, I would just like to say a big thank you to Vice President of Marketing at GreenWaves, Martin Kroon, and CTO and co-founder of Augmented Hearing, Martin Bergman. Thank you very much for joining us today. I am the event and project manager on behalf of Danish Sound Cluster. I would like to say thank you for joining us. We are a member organization in the sound industry. We are facilitating the sharing of knowledge, experience, and new research, relationship building in the sound community, and new collaborations to boost innovation. You can follow us on YouTube for loads of webinars, where this one also will be uploaded if you missed any of the action. And you can follow us on LinkedIn for future events and webinars. Here are just a few of our upcoming webinars and events, physical events as well. So you can have a look at our event section on our website. Now, if you would like to collaborate, and if you are inspired by this collaboration talk today by Martin and Martin, please reach out to us if you are working in health and hearing, acoustics and environment, or sound experiences. We would love to hear from you if you have any new project ideas, and please contact our project manager, Tine Midgaard, on email or phone, and she'll be happy to hear from you. Now, there's nothing left to say, but thank you very much for all of you joining us in the audience, and thank you, Martin Bergman and Martin Kroom, for joining us at Danish Sound Cluster today. It's been a huge pleasure, and I hope to see all of you some other time. Thank you.
Thank you.
Bye-bye.
Bye.